So if we're going to differentiate between a polar and a non-polar covalent molecule, the first thing I think is to first mention what is a covalent molecule. A covalent molecule is when electrons are shared between two atoms. Now, when they are evenly shared, you then get a non-polar covalent molecule. And if they are unevenly shared, you get a polar covalent molecule. So if we want to explain that, let's take something like hydrogen. Hydrogen has got one valence electron. Another hydrogen would have one valence electron. They would share that pair. The electronegativity of one hydrogen is 2,1 and the other is 2,1. And therefore, they are going to share that electron pair completely evenly between the two of them. And one side of the molecule won't be more positive or more negative than the other side. That's non-polar. The next one is, let's take something like hydrogen chloride. Chlorine has got 7 valence electrons. Hydrogen has got 1. They share those electrons. Chlorine's electronegativity is going to be a whole lot higher than hydrogen's. So therefore, what's going to happen is if they're tugging of warring over these two electrons over here, those electrons are going to spend more time with the chlorine. That means that this whole electron cloud and this molecular orbital is actually spending more time on the chlorine side of the molecule. That results in the chlorine side of the molecule being slightly negative. The electron hasn't been transferred, so it's only slightly negative, and the hydrogen side being slightly positive. That is a polar covalent bond. If I'm asked to use Lewis dots to represent a water molecule and magnesium chloride bonding, the first thing that I need to do is I need to consider whether they are covalent or ionically bonded. Now, water is between oxygen and hydrogen, so those are both nonmetals. Oxygen has got 6 valence electrons because it is in group 6. And hydrogen has got 1 valence electron, it's in group 1. And I land up with a sharing situation that looks like that. Get a polar covalent molecule with the oxygen side being slightly negative and the hydrogen side being slightly positive. I don't have to do that when all they've asked me to do is a Lewis dot diagram. With magnesium chloride, it's magnesium and chlorine. Magnesium is a metal, chlorine is a non-metal, so I am going to have magnesium with its 2 valence electrons, chlorine with its 7, I better do those as dots, 7 valence electrons. 1 electron is transferred to the chlorine, and if we do that again, the second electron is transferred to the chlorine from the metal to the non-metal. And then I am going to write Mg is now short of 2 electrons, so it's 2 plus. The chlorines have each gained an additional electron, so they're negatively charged, and they now have a negative charge, and there are 2 of those chloride ions. Number 6, what intermolecular forces exist between the following substances? We've got hydrogen molecules, water molecules, hydrogen chloride molecules, sodium chloride molecules, and copper. The first thing is that the sodium chloride and copper actually don't form molecules. They're going to form lattices. The copper is going to form a metallic lattice. So if I need to say what holds it all together, not quite what is the intermolecular force, it's really what forces hold the lattice together, it's going to be a metallic bond. With sodium chloride, again, I don't have a real molecule. I have got an ionic lattice. That lattice is going to be held together by plus ions, so the cations holding on to the anion. So it's an electrostatic attraction between ions, and therefore if I needed to be pushed to say what holds the lattice together, I would say it is actually an ionic bond. The remaining ones are all actually molecules, so let's think about it. Hydrogen chloride, we've just done hydrogen chloride over here, and we agree it's a polar molecule. It's a polar covalently bonded molecule. So what's going to hold together, this creates something that we call a dipole. It's got two poles, a positive pole and a negative pole. So the dipoles hold together, slightly positive, slightly negative. What holds the next molecule? Slightly negative, slightly positive. We land up with an attraction between slightly positive and slightly negative. That is known as a dipole-dipole van der Waals force. If I'm looking at a water molecule, we've got a water molecule over here, we can see again that we've got a dipole. But water is, oxygen is one of my NOx gases. So there are three substances that you need to know now that have got hydrogen bonding or hydrogen bond forces. One is HF, one is NH3, and the other one is H2O. So the minute you see water, an alarm bell goes off, bee-bar, 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 and you think, whoa, I need to consider hydrogen bond forces as my intermolecular forces. Why? Because fluorine, nitrogen, and oxygen are all very small atoms with very high electronegativities. So they can attract each other uncharacteristically tightly together. You get generating the strong intermolecular force of a hydrogen bond force. Finally, a hydrogen molecule. We've drawn a hydrogen molecule up here already, and we've decided it was completely nonpolar. So if there's nothing positive and negative on any side of this, how's it going to hold together? There are going to be instantaneous dipoles. So for a split second, you can either call it a London force, an instantaneous dipole, a snapshot dipole, a momentary dipole, but just for a second, one side becomes slightly positive, the other side becomes slightly negative, and the neighboring molecule has the same thing happening. All just happens for an instant and then rearranges. This is a particularly weak force of attraction, and because of that, we land up with substances that have very low melting and boiling points. Taking a look at number 7, what is the shape of the following molecules? Tetrachloromethane, ammonia, water, carbon dioxide. So our water is easy, it's right here. It's an angular shape. We can see very clearly that these two electron pairs are going to repel the hydrogen atoms downwards a little bit inside the molecule, drawing out some of the other molecules. First, the tetrachloromethane. We're going to go carbon in the middle, tetra, chloro, methane. This is one of those completely symmetrical molecules. It's symmetrical in 3 dimensions, and even though I have polar bonds, I land up with an overall non-polar molecule, and the shape is tetrahedral. Ammonia, nitrogen, hydrogen, 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 and I have a shared electron pair at the top over there. It's not shared, a lone electron pair, and it repels these hydrogen atoms down slightly with electron repulsion, and I therefore land up with a shape that is called trigonal pyramidal. Water we've discussed is angular, and finally carbon dioxide. If I'm going to draw out the carbon dioxide, it's carbon in the middle, double bond O, no lone pairs in either of those places, and I land up with a linear molecule. Last one, draw and label an energy profile diagram for an endothermic reaction. We did one for an exothermic reaction. You need to write reaction coordinate. And you need to have the potential energy. You should write that out in full and put kilojoules as a unit. And my endothermic energy profile has the reactants with less energy than the product. If I'm going to label it completely, this is my activated complex. This over here would be my reactants. products. Maybe over here put in the delta H, or the heat of the reaction, and maybe over here we might want to write activation energy. And there is our endothermic classic curve.